4. Correlational and predictive techniques. Biomedical research often seeks to establish whether there is a relationship between two or more variables. For example, is there a relationship between salt intake and blood pressure, or between cigarette smoking and life expectancy? The methods used to do this are correlational techniques, which focus on the correlatedness of the two variables. There are two basic kinds of correlational techniques. One, correlation, which is used to establish and quantify the strength and direction of the relationship between two variables. Two, regression, which is used to express the functional relationship between two variables so that the value of one variable can be predicted from knowledge of the other. Correlation. Correlation simply expresses the strength and direction of the relationship between two variables in terms of correlation coefficient, signified by the letter R. The values of R vary from -1 to +1. The strength of the relationship is indicated by the size of the coefficient, while its direction is indicated by the sign. A plus sign means that there is a positive correlation between the two variables. High values of one variable, such as salt intake, are associated with high values of another variable, such as blood pressure. A minus sign means that there is a negative correlation between the two variables. High values of one variable, such as cigarette consumption, are associated with low values of the other, such as life expectancy. If there is a perfect linear relationship between the two variables so that it is possible to know the exact value of one variable from knowledge of the other variable, the correlation coefficient R will be exactly ±1. If there is absolutely no relationship between the two variables, so that it is impossible to know anything about one variable on the basis of knowledge of the other variable, then the coefficient will be zero. Coefficients beyond plus or minus 0.5 are typically regarded as strong, whereas coefficients between 0 and plus and minus zero point 0.5 are usually regarded as weak. USMLE does not require the actual calculation of R. Scattergrams and bivariate distributions. The relationship between two correlated variables forms a bivariate distribution, which is commonly presented graphically in the form of a scattergram. The first variable, salt intake, cigarette consumption, is usually plotted on the horizontal x-axis, and the second variable, blood pressure, life expectancy, is plotted on the vertical y-axis. Each data point represents one observation of a pair of values, such as one patient's salt intake and blood pressure, so the number of plotted points is equal to the number of size n. Figure 4.1 shows 4 different scattergrams. Determining a correlation coefficient involves mathematically finding the line of best fit to the plotted data points. The relationship between the appearance of a scattergram and the correlation coefficient can therefore be understood by imagining how well a straight line could fit the plotted points. In figure 4.1a, for example, it is not possible to draw any straight line that would fit the plotted points at all. Therefore, the correlation coefficient is approximately zero. In figure 4.1b, a straight line would fit the plotted points perfectly, so the correlation coefficient is 1. Figure 4.1c shows a strong negative correlation, with the correlation coefficient in the region of negative 0.8. And figure 4.1d shows a weak positive correlation of about plus 0.3. Types of correlation coefficient. The two most commonly used correlation coefficients are the Pearson product moment correlation, which is used for interval or ratio scale data, and the Spearman rank order correlation, which is used for ordinal scale data. The latter is sometimes symbolized by the letter rho. Pearson's R would be used, for example, to express the association between salt intake and blood pressure, both of which are ratio scale data, while Spearman's rho would be used to express the association between birth order and class position at school, both of which are ordinal scale data. Both these correlation techniques are linear. They evaluate the strength of a straight line relationship between two variables. If there is a very strong non-linear relationship between two variables, the Pearson or Spearman correlation coefficients will be an underestimate of the true strength of the relationship. Figure 4.2 illustrates such a situation. A drug has a strong effect at medium dosage levels, but very weak effects at very high or very low doses. Because the relationship between dose and effect is so nonlinear, the Pearson R correlation coefficient is low, even though there is actually a very strong relationship between the two variables. Visual inspection of scattergrams is therefore invaluable in identifying relationships of this sort. More advanced nonlinear correlational techniques can be used to quantify correlations of this kind. Coefficient of determination. The coefficient of determination expresses the proportion of the variance in one variable that is accounted for or explained by the variance in the other variable. It is found by squaring the value of r, and its symbol is therefore r squared. So if a study finds a correlation r of 0.40 between salt intake and blood pressure, it could be concluded that 0.40 times 0.40 is equal to 0.16, or 16% of the variance in blood pressure in this study is accounted for by variance in salt intake. A correlation between two variables does not demonstrate a causal relationship between the two variables, no matter how strong it is. Correlation is merely a measure of the variables' statistical association, not of their causal relationship. So the correlation between salt intake and blood pressure does not necessarily mean that the changes in salt intake caused the changes in blood pressure. Inferring a causal relationship between two variables on the basis of a correlation is a common and fundamental error. Furthermore, the fact that a correlation is present between two variables in a sample does not necessarily mean that the correlation actually exists in the population. When a correlation has been found between two variables in a sample, the researcher will normally wish to test the null hypothesis that there is no correlation between the two variables, that is, that R is equal to 0 in the population. This is done with a special form of t-test. Regression. If two variables are highly correlated, it is possible to predict the value of one of them, the dependent variable, from the value of the other, the independent variable, by using regression techniques. In simple linear regression, the value of one variable x is used to predict the value of the other variable y by means of a simple linear mathematical function. The regression equation, which quantifies the straight line relationship between the two variables. This straight line or regression line is actually the same line of best fit to the scattergram as that used in calculating the correlation coefficient. The simple linear regression equation is the same as the equation for any straight line. Expected value of y is equal to a plus bx, where a is a constant known as the intercept constant because it is the point where the y-axis is intercepted by the regression line. In other words, the value of y when x is 0. B is the slope of the regression line and is known as the regression coefficient. It shows the change in y when x increases by 1 unit. X is the value of the variable x. Once the values of a and b have been established, the expected value of y can be predicted for any given value of x. For example, it has been shown that the hepatic clearance rate of lidocaine Y in milliliters per minutes per kilograms can be predicted from the hepatic clearance rate of indocyanine green dye x in milliliter per minute per kilogram according to the equation y is equal to 0.30 plus 1.07x, thus enabling anesthesiologists to reduce the risk of lidocaine overdose by testing clearance of the dye. Multiple regression. Other techniques generate multiple regression equations in which more than one variable is used to predict the expected value of y, thus increasing the overall percentage of the variance in y that can be accounted for. A multiple regression equation is therefore expected value of y equaling a plus b1 times x1 plus b2 times x2 plus whatever, but as long as any b number of b's times any numbers of x. For example, Angulo et al. In 2007 found that the risk of hepatic fibrosis, Y being the patient's fibrosis score, in patients with non-alcoholic fatty liver disease could be predicted on the basis of the patient's age, body mass index, presence of diabetes or impaired fasting glucose, aspartate aminotransferase or alanine aminotransferase ratio, platelet count, and albumin level according to the multiple regression equation. So when you calculate that, uh, you crunch up the numbers. Um, okay, y is equal to negative 1.675 plus 0.037 times age in years plus 0.094 times the BMI in kilograms per meter square plus 1.13 times presence of IFG or diabetes, yes equaling 1 and no equaling 0, 0.99 times the ratio of AST over ALT minus 0.013 times platelet count times 10 to the ninth power per liter minus 0.66 times albumin in grams per deciliters. Use of this regression equation was shown to allow a liver biopsy to be avoided in the majority of patients of non-alcoholic fatty liver disease, a disorder that is found in substantial proportion of Western populations. Multiple regression can also be used to search for other potentially confounding contributors to um, use of this regression equation was shown to allow a liver biopsy to be avoided in majority of patients of non-alcoholic fatty liver disease, a disorder that is found in substantial proportion of Western populations. Multiple regression can also be used to search for other potentially confounding contributions to the condition of interest. If data on multiple other variables are collected, regression techniques would allow their contribution to the left side of the equation to be included. If in doing so, the coefficients of the variables of interest change, then these variables have automatically been adjusted for the presence of the new and apparently confounding factors. If the coefficients do not change, then the new factors have no influence and are not confounders. If the coefficient of any variable approaches zero, it clearly plays no role in the outcome of interest and can therefore be removed from the equation. Logistic regression. In linear regression, y can theoretically have any possible value. In many situations, however, we are not interested in a numerical outcome such as the risk of fibrosis, but in a nominal or categorical one, typically a binary or dichotomous one, such as death versus survival, developing lung cancer versus not developing lung cancer. Here, the relationship between risk factors and the outcomes is clearly not a linear one. While exposure to a risk factor increases gradually, the change in outcome from survival to death or from health to a diagnosis of cancer is a sudden all or nothing one. Hence, the outcomes such as death versus survival are conventionally represented by 0 and 1. A mathematical function, a logistic function, is used to transform the linear regression data so that the values of y are limited to the range of 0 to 1, giving us the probability of the outcome y occurring like any probability. It can range only from 0 to 1 for given values of x. Just as with multiple regression, coefficients show the strength of the influence of different factors. Some factors may have a very low coefficient, showing that they are not significant predictors of the outcome. For reasons beyond the scope of the USMLE, logistic regression is particularly suited to the analysis of case control studies, telling us the odds of the outcome of interest, such as death, versus its converse, such as recovery, for a given degree of exposure to various risk factors, as well as the p value associated with this finding. For this reason, logistic regression is used very commonly, particularly in public health and cancer research. For example, D'Souza et al. In 2007 compared patients' cases with newly diagnosed oropharyngeal cancer with otherwise similar clinical patients controls who did not have cancer. A logistic regression analysis showed that multiple risk factors, HPV-16 seropositivity, poor definition, infrequent toothbrushing, family history of squamous cell carcinomas of the head and neck, and heavy tobacco use were significantly associated with the development of this cancer, accounting for the development of 90% of cases. Survival analysis. A further technique for analyzing data about binomial outcomes such as death versus survival or cancer versus low cancer is provided by survival analysis, rather than merely looking at the proportion of patients who die or survive, or at the likelihood of death or survival following exposure to various risk factors or treatments. Survival analysis addresses questions to do with the time to event data, such as what is the survival time of patients with a given disease? How does the survival time compare between two groups of patients given different treatments for the same disease? Among those who survive up to a certain time, at what time or rate can they be expected to die? What factors, such as risk factors or treatments, affect the survival time? Despite its name, survival analysis can be used to help answer questions of this kind about any kind of event, not just death, such as how long it takes before a hip replacement fails, how long it takes before a patient has a second heart attack, or how long it takes for a coronary stent to become restenosed. And it is widely used outside medicine in fields such as engineering. How long is a hard drive or light bulb likely to survive? For example, a study of the survival times of patients with newly diagnosed prostate cancer might aim to discover the following. How long do patients with treated and untreated prostate cancer survive after diagnosis? What variables, risk factors, and treatments affect survival time, and to what extent changes in each variable affect survival time? Answering the first question appears simple. However, the mean or median survival time of treated and untreated prostate cancer patients cannot be determined for a number of reasons. The most obvious of which is the data from patients who are still alive at the end of the study is excluded unless we continue to gather data until all patients are dead, which is not usually practical. Furthermore, some patients may be lost to follow up, and others will die not of prostate cancer but of unrelated causes. Omitting data from these patients would clearly bias the estimate of survival time. Such items of data are called censored observations, meaning that the event of interest had not occurred or the data was not available by the time the data was gathered. The simplest technique in survival analysis is life table analysis. A life table tracks lives for the event of interest, such as death, in a group of people from a time when none of them have experienced the event until the end of the study, when data is no longer being collected. To analyze it, we divide the period under study into a certain number of equal intervals, such as 60 monthly intervals. For each of these intervals, we record the number of people who entered that time period alive and the number who died during that time period, as well as the number of people who were lost to follow up or censored during that same period. This allows us to calculate the survival function, which is the cumulative proportion of patients surviving at any particular time t. In other words, the probability of surviving beyond that time. Survival function at time t is equal to number of patients surviving longer than t divided by total number of patients. This calculation is called Kaplan-Meier analysis. The survival function is recalculated each time an event such as death occurs. The median survival of a group of people is the time when the survival function is zero point 0.5. This is the same as the 50th percentile for survival time. In a similar way, 25th, 75th, or other percentiles can be found. Note that the survival function solves the problem of censored observations, as it does not require knowing the survival time of every member of the group. Note also that the median or 50th percentile survival time will not be the point at which 50% of the patients have survived, unless there had been no censored observation until this time. Live table analysis also allows us to estimate the likelihood of further survival at any time. Example, if a patient has survived for 3 years since diagnosis of prostate cancer, how likely is he to survive for a further 3 years? Live table data and the survival function are commonly shown graphically by means of a Kaplan-Meier plot, which is the commonest type of survival curve. Although it actually although it is actually a series of steps rather than a curve, as the proportion of people surviving changes discretely when the event of interest occurs. This plot shows the proportion of people surviving for any given length of time. Often there will be two or more groups of patients, such as those who were treated and those who were not treated, or those given treatment A versus treatment B. And also there and so there are two or more curves. This is seen in figure 4.3, which shows the proportions of under 65-year-old patients with established coronary heart disease who survive for the first 6 years after randomization to a statin drug, simvastatin, versus a placebo in the well-known 4S study, the Scandinavian simvastatin survival study. The effect of a factor such as treatment is shown by the difference between the two curves. If the curves overlap or are very close, the difference between the treatments is unlikely to achieve statistical significance. Specialized forms of the chi-square test, such as the log rank test, also known as the Mantel-Haenszel test, are used to test the null hypothesis that there is no difference between the two survival curves in the population. Note also that the distinction between the two curves is a nominal or categorical one: treatment versus placebo, or treatment A versus treatment B. The second question in our cancer study, for example, what variables such as risk factors or treatments affect survival time, and to what extent do changes in each variable affect survival time, cannot be answered by a life table or Kaplan-Meier's analysis, as it goes beyond asking about the effects of a nominal scale variable, treatment versus no treatment, treatment A versus treatment B. This second question is similar to the questions that are answered by multiple regression and logistic regression techniques, in which a series of explanatory variables x1, x2, x3, etc. are used to predict the value of variable y. However, neither multivariate regression nor logistic regression can be used to answer this question, because neither of them can deal with the problem of censored observation, and logistic regression can only predict the probability of death, the outcome y, but cannot predict the likelihood of survival to a particular time, or the extent to which changes in each variable affect the likelihood of survival to a particular time. A special regression techniques, Cox regression, overcomes these problems. Like the regression techniques, it produces an equation for the outcome y, likelihood of survival to a particular time, as a function of several explanatory variables x1, x2, x3, etc., such as treatment, patient age, tumor stage, etc., simultaneously, and it allows us to see the strength and direction of the relative contributions of these variables in the form of the coefficient for each variable. This technique is also known as Cox proportional hazards analysis, because it shows the degree to which changes in the independent variables affect hazard, also called hazard rate, the risk that an event such as death will occur at a given time, given that it has not occurred up until that time. By looking at the hazard rates for different groups of patients, such as treated versus untreated patients, Cox regression can produce an estimate of the hazard ratio. This is the ratio of the risk of the event at a particular time, the hazard, in the exposed group to the hazard in the unexposed group. For example, the hazard ratio for death from treated versus untreated prostate cancer 5 years after diagnosis might be zero point 0.5, meaning that the treated patients are only half as likely to die at that time. Cox regression is therefore commonly used in clinical trials and in cohort studies. A typical use of Cox regression was in the well-known seven-country studies Jacobs et al. In 1999, in which a cohort of over 12,000 middle-aged European, American, and Japanese men were followed for 25 years. Their smoking habits, country of residence, age, BMI, serum cholesterol, systolic blood pressure, and clinical cardiovascular disease were recorded. After adjusting for each of the other variables, the hazard ratio for death due to any cause in those who smoke less than 10 cigarettes per day versus never smokers was 1.3. It was 1.8 for those who smoked more than 10 cigarettes per day. Hazard ratios were also elevated among smokers versus never smokers for death due to, among other things, coronary heart disease, stroke, and lung and other cancers. P-values were reported for each of these ratios, showing that they were unlikely to have been due to chance. Hence, the study confirmed that smoking is an independent risk factor for death due to these diseases. Choosing an appropriate inferential or correlational technique. The basic choice of statistical technique for analyzing a particular set of data is determined by two factors: the scale of measurements and the type of question being asked. USMLE will require familiarity with only those techniques that have been covered here, although there are many others. Table 4.1 summarizes the choices. Concerning nominal scale data, two kinds of questions have been discussed. Do the proportions of observations falling in different categories differ significantly from the proportions that would be expected by chance? This technique for such questions is the chi-square test. Questions concerning predictions. What is the likely outcome, such as life or death, sickness or wellness of exposure to given risk factors? The technique for such questions is logistic regression. Regarding ordinal scale data, only one kind of question has been covered. Is there an association between ordinal position on one ranking and ordinal position on another ranking? The appropriate technique here is the Spearman rank order correlation. For interval or ratio scale data, two general kinds of questions have been discussed. Questions concerning means, such as what is the true mean of the population, or is one sample mean significantly different from another sample mean? To answer this, a t-test will normally be used, alternatively provided that n is greater than 100, or if the standard deviation of the population is known, a z-test may be used with virtually identical results. Questions concerning association prediction, such as to what degree are two variables correlated. To evaluate the strength and direction of the relationship, Pearson product moment correlation is used together with a form of t-test to test the null hypothesis that the relationship does not exist in the population. So here we have table 4.1. And here are the different questions that concern differences in proportion, which will be used using the chi-square test for nominal data. One or two means, we would use a t-test or z-test if n is greater than 100. Association, you use the Spearman rho or Pearson R. Predicting the value of one variable, you use if it's on the basis of one or other variable, you use the simple linear regression, or if it's on the basis of multiple variables, you can use multiple regression. Logistic regression, predictor variables are ratio data, predicted variable is nominal. And predicting survival time, you just use Cox regression, interval or ratio data. And the question is, what is the predictive value of one variable given values of one or more other variables? To make predictions about the value of one variable on the basis of one other variable, simple linear regression is used. If the prediction is to be based on several variables, then multiple regression is used. If the prediction is about survival time to an event, Cox regression is used. So the key point here is to remember this table 4.1, which is summarizing the range of inferential and correlational techniques that have been covered. We should memorize this table to answer any typical USMLE questions that require the choosing of the correct answer or technique for a given research situation. So know this table code.